right, I see some responses on the chat. Thank you all. I'll just wait until Austin puts up the presentation before starting to talk. Well, I guess I don't have to wait entirely, but just to say thanks again to Austin and the BioGears team for adapting and keeping the conference going despite all the social distancing. My name's Adamos-Binks. I'm the Chief AI Scientist at Applied Research Associates, which both has the BioGears contract and has some other work that is contracted to JPC1. I really enjoyed the keynote this morning from Professor Miller. It was a great talk and a really serendipitous setup for our talk. Since I started at ARA, I've always been looking for opportunities to collaborate with the BioGears team. And so this other project I was working on called 4TDS started hitting some hard limits on our machine learning model performance. So we started to investigate how a digital twin collaboration might look with BioGears. So you can go to the next slide, Austin. So there's lots of definitions for digital twin, but from my perspective, and I think Professor Miller kind of articulated this morning, it really comes down to a simulation trade-off. So what's the fidelity of the signal you need to get from the real-world object and store it so you can simulate it? The digital twin concept sort of first originated in manufacturing engineering for product lifecycle management. So it was purely functional goal. There was one component that they had sensors on, and they were trying to do sort of preventative maintenance on it. If you click to the next animation there, Austin, perfect. Next, people started thinking about applying this to healthcare. So the immediate application, or most obvious one, was to a hospital. So create the digital twin of a hospital so you could simulate things like demand for supplies, scheduling of operating rooms, of people, understand who's been in contact with who for diseases. Next up, thanks for going ahead there. I think the next evolution of this digital twin concept is to biology, to human biology. But I think it's the hardest one because we don't have a lot of the underlying equations. We've got some. We just heard a great talk from Matt about some of them, but it presents some particular challenges because we can't always account for all the things going on in the human body in the equations. And then on the other side of modeling, we also don't have a lot of clean data. So we're going to start hitting hard limits on learned model performance. So machine learning and data science approaches are also going to start hitting this limit. So I think the path forward here on simulating biology is using machine learning models and mechanistic models to realize this vision. So that's a very hard problem, and you see the quote down at the bottom of the screen. So this is if you don't know, Donald is a very famous computer scientist. He's won tons of awards and made some really landmark discoveries in computer science, and he's fascinated by biology and thinks there's tons of hard problems. I do too, not that means anything when he says it. But you really need this mix of expertise to make this happen, to really understand the problems both on the machine learning side and the mechanistic models. And luckily, Christie Burris works at ARA. So she's gotten her hands dirty with data-driven models on the 4TDS project, which you hear just a little bit about in this, and also has a background in applied math. So what this talk is from here on out is sort of what I think, framed in Professor Miller's words, is first steps to a digital population study. So I'll hand it over now to Christie, who's done all the work and has lots of interesting things to say on how we might do this. So go ahead, Christie.
Okay, thanks, Adam. We'll move right along here. So yeah, I just want to echo one more time how nicely the previous presenters have really started us off. And I think, like we said this morning, we really think of data as a commodity as well. And Adam and I work on a project here at ARA that uses machine learning to tackle some of these same questions that we've been talking about all morning, how to bring better prolonged field care, decision support, things like that. So we're going to relate that back to our original project and keep going with some of these overarching themes of modeling in that context. So I want to start by providing this figure of how we view the current state of predictive modeling. And I just want to say current state is a little bit vague. There's clearly a lot of research going on in this area already, but I see these two paths of machine learning and mechanistic modeling moving in parallel tracks without much overlap. So I think of BioGears in this mechanistic modeling sense, being based on first principles, solving these really difficult computational tasks, and then the current project that Adam and I work on for TDS is really concerned more with this observational data analysis. And oftentimes in decision support, we see image classification and things like that. But we really want to spend the rest of the talk talking about how we plan to bridge this gap and to really bring these two types of predictive modeling together. So we see both of these modeling strategies having sort of opposite pros and cons. So for the machine learning side of things, the real advantage is speed. If we can take the training offline and do that kind of work behind the scenes, it makes these machine learning models available in real time to patients and casualties and medics doing this kind of decision support. But on the flip side, this stuff is not driven by first principles. We're looking at observational data. We made the comment about electronic health records in the previous question. This is the data that we use, and it requires a large amount of that kind of data. So on the flip side, with mechanistic modeling, like here at BioGears, we do have this user trust in the model that's driven by first principles, because this is what experts are familiar with and that they trust. But like we've been talking about, it's not, the computational speed is not there to do these kinds of simulations in real time. And as we can see, these things are so mathematically complex that they can be limited in scope to certain parts of the body, and we really want to make this a holistic experience for people in the simulation world. So our real goal is to bridge the gap between these two types of modeling, and that takes the form of trying to get a machine learning model to learn these first principles in an effort to reduce the computational time of these really difficult modeling tasks. And in that way, when we can bridge this gap, we get rid of these cons that we see, these kind of limitations of the current modeling paradigm. So that brings us to Adam and I's current project for TDS, and I'll briefly describe what we do and how it relates to BioGears in the first place, why we found ourselves at this collaboration, and then I'll just go into detail about how we collaborated with BioGears to create a feature that we found really useful for our current modeling problems. So 4TDS stands for Trauma Triage Treatment and Training Decision Support. Why I didn't put the whole acronym on here. Our goal is to improve combat casualty experience by giving combat medics the quality and efficiency of our healthcare support network. And we do this by creating models. So we call it health, IT, and data analytics. But what it really means is that we're trying to build a machine learning model from this electronic health record, from ICU admissions in the hospital, to build a septic shock detection model. So eventually, this model will get deployed onto a tablet that a combat medic can bring with him to support a particular decision that he will eventually have to make in the battlefield. And we do this by this is some jargon feature engineering, but really that just means that we do some mathematical tweaking, so to speak, to capture the physiology changes that manifest themselves in septic shock to try to build a machine learning model that recognizes those patterns and helps bring this decision support. But along with that, there we go. We experience a lot of challenges. For instance, I just want to speak briefly about the data because this is the challenge that we're tackling with BioGears. So we're using electronic health records, as we mentioned. We call them EHR, and as I think we now know, this is your comprehensive medical history across the healthcare system. So if you go into the hospital and you get lots of tests and you get sent to the ICU, you come back out, this is all recorded in your unique electronic health record. And I just want to mention that this is designed entirely for billing purposes. And with that comes a lot of limitations because an insurance company is not terribly concerned with the research that we do. So these challenges that arise come in the form of not having controlled experiments. So that just means that a lot of the results that we see are really ad hoc. A clinician is not going to order a blood sample unless they suspect some kind of issue. So we get a lot of ad hoc results because we're not working with clinical trials. And on top of that, we get a lot of missing or noisy data. I have a figure here, if we can look at the slides. For heart rate, maybe these little dots are not, you can't see them very well, but I'm trying to indicate that the frequency with which we see readings coming in is not uniform, and this happens all the time. So when we're trying to capture change over time, this is a really big issue that we face. And there are a lot of other things in this missing noisy data category, but you can extrapolate and imagine what we could be working with. And then the last thing is that we have imbalanced classes because we're working again with observational data, which means that not 50% of our population is sick with septic shock. So we're working. These are issues that a machine learning model that we need to address when building a machine learning model. And we see a means of improving these solutions while also paving a path for this overarching goal of really bridging the gap between these two types of modeling strategies. So right now, most of these challenges that we face, we use off-the-shelf techniques to solve, and that's totally fine, but we really see a means of pushing innovation while improving these problems, which means that the long-term goal of this particular collaboration at the moment is to enhance our data sets with BioGears simulations in an effort to bolster our training set that we're using to train this model to detect septic shock. So what that means is we're going to be simulating a lot of infections in BioGears and trying to match what we see in real patients, because obviously these two things, simulations and real observational data, they're going to manifest quite differently, but we want to give ourselves a read of how close these are and how we can build upon each of them by this collaboration. And we think that we're positioned to do this because we have all the expertise in-house. We have the data on both sides, observational and mechanistic, and we think that we have a good team to really go back and forth with these ideas, because I think one of the pervasive themes is that it really takes a back and forth dynamic of learning from each other, from these two different scenarios. And we're grateful that we have the development resources to make that happen. So what that looked like in terms of this project that was incepted a couple of months ago, we're in the first stages, is really to just get a sense for what's possible. And we asked ourselves a couple of questions. The first was a motivation for improving the data on our own projects on 4TDS. So we wanted to know if we could generate simulations in BioGears that match the trends and level of variation that we see in ICU patients. Because it's really clear, just on that previous talk that Matt gave, how nicely continuous these systems are, how smooth and just, I mean, they're quite beautiful, but they're very different from a patient who has come in, who's been smoking their whole life, who's maybe, you know, drunk and needing, I don't know, needing some assistance, that has all sorts of comorbidities, right? We're looking at a really different thing. So we want to know if it's feasible to bridge these two things. And then on top of that, in terms of our larger goal to really incorporate machine learning into these physics-based models, we want to know if we can get simulations that span the solution space of the underlying physiology model, because this is going to be really important in developing machine learning algorithms for BioGears in the future. So with those two feasibility studies, so to speak, in mind, we set out trying to create a pathway through the BioGears build to make that happen. And we had help from people on the BioGears team here at ARA. They built me a patient generation feature. I was really grateful for this because it would have taken me a long time to individually create a data set that we want to be quite big. But this is found under the examples in BioGears, and what I did was offer this feature a CSV file with parameters that will eventually vary the type of, or maybe not the type of infection, but the infection parameters that we just went over in that sepsis model. And then I also vary the patient state file. And I really want to hit home that varying the initial state of your patient can create a lot of variability. So given that that input, I can ask for, you know, 1,000 or however many scenarios to be run in a batch. And what I get out is a bunch of the CSV data requests that I've asked for each of the scenarios that I've passed from that input file. And these come, I ask for data requests that are relevant to septic shock, and then I look for them. So we iterated several times on that process of using the how-to feature, and I maybe want to transition into talking about how BioGears is quite a bit different from EHR, because it requires a lot of tweaking to go from, maybe I should say tweaking in the form of creating actions and complexities like comorbidities and pre-existing conditions to really generate anything that looks similar to a patient in the real world. So that's what I spent most of my time doing, trying to figure out how to really match simulations to the data that I already have. And then there was a bit of post-processing because our future goal is to make this data set available, and I shouldn't say future, we got it out today. It'll be up on GitHub today, something we're very excited about, but there's a bit of post-processing to get these CSV files into a shape that matches what we see when we receive electronic health records. So let's talk about some results that we see, just to conclude here. I just want to say these results are really promising. And I had a fair deal of skepticism going into it. As an applied mathematician, I also understand how separated my work is from the real world, but I just want to say how exciting it was that this kind of work really paid off. So in order to match the shape of a lot of the progression of diseases and vitals that we see with our EHR data, which I should say comes in the form of vital readings in an ICU admission. So I'm looking at heart rate and blood pressure, things like that, biomarkers that I care about over time. And what I saw is that by simulating BioGears, I found similar shapes of these progressions over time, which was really promising. And while they don't look exact, you can look at these two pictures. Obviously, the progression time is a little bit different. I really see a path forward iterating and being able to bring these closer in similarity, which means that really the next steps, I feel, are to quantify what this similarity, what I mean by similarity. How do I know that these two things present the same without having to look at the data myself, because I'm going to want to do this with millions of samples. So the next steps are to quantify how these two different data sets are similar or different. But I just want to point out really promising results in that way. And that comes mainly from this slide that I have here with these two different figures next to one another. When I first started, I was a little nervous because as you see how smooth and really perfect these curves are, and if you don't do anything and run a bunch of simulations of sepsis without any action apart from maybe feeding a person, you see this thing on the left side, which is really structured and nice. But this is not how patients manifest themselves, as I said. But just by creating and inducing actions like pain, stress, and exercise, as you see on this right figure, I created something that honestly looks very similar to a patient sitting in a hospital. And while we don't see the general trend of moving upward with heart rate near a septic shock state, I really see this, this approach of adding these actions in at some random interval really promising. And so these two slides here answer the question of whether or not BioGears can be well integrated into the EHR data to help us supplement in a real-time current project to increase the accuracy and scope of our deployed machine learning model to diagnose septic shock. But then to step back a little bit and go back to the original sort of overarching theme of trying to bridge two types of predictive modeling, I wanted to know if I could generate a bigger solution space than just a single curve with these BioGears simulations. And I feel really grateful to say that it worked out quite easily and sooner than I thought. So what you're looking at is two pictures of a lot of simulations in BioGears. Maybe I chose 20 just so that you could see it. But all of these are a progression of a simulation in BioGears. I'm looking at the diastolic blood pressure and core temperature, two really important diagnostic tools when looking at septic shock. And all I did was randomize an initial patient generation. So I changed their starting heart rate, blood pressure, things like that. And what you can see is that we see a lot of variation, which is really nice. And even though with diastolic blood pressure, maybe we don't see as much variation as we do with core temperature and overall shape, I do want to mention that this change in the slope of these curves and the rate of change is actually quite significant and really nice. So what came of this is really that these feasibility studies, shouldn't call them studies, just little things that we tried to do, were really promising. And so to wrap up, while we haven't necessarily gotten ourselves to any of those original goals of trying to actually supplement this data set to increase the accuracy of our model, we do plan to do that in the near future when we get enough data built up from BioGears simulations. So that's what this first bullet is. We're going to supplement that data set with BioGears data, and then we have some obvious metrics for understanding whether or not that project was successful. And then beyond that, we imagine generalizing to other scenarios. So once we build this data set for septic shock, a million other things that we could simulate with BioGears. And that brings us to this notion of physics-based machine learning research, which I think is where we're headed. And it's by capturing the underlying mechanics of BioGears with a machine learning model, we really open up the possibility of being able to take BioGears offline and make it something that we do, that we can simulate in real time, which I think is really amazing and matches a lot of the goals that I think we've been talking about all day. So just to wrap up, we got the development team here to build us a new BioGears feature, which is in development, that has enabled us to do this data set creation. And we're proud to say that we have about 50 samples up now on GitHub that we want to share with people. And we imagine that there will be a lot of other future use cases for these kinds of data sets, because we see this, this field of predictive modeling really coming together and doing some amazing things. And then something that we didn't get to talk about in this presentation, but that I'll briefly plug, is that we've always imagined really using this decision support to promote smart resource management, particularly in the context of multi-casualty care on the battlefield. And we really see that as another next step for this kind of work. And I'll just briefly mention that I'm really impressed with with BioGears and the work that they're able to do, because as I might have mentioned earlier, as a mathematician, it's hard to imagine moving out of a theoretical realm into something that people really tangibly use, that people see as really important. And I think this is a really clear example of that. So thank you. Love to take any questions.
All right. Thank you, Christie. That was really, really excellent. I think that this application has just a ton of potential. And I remember when we were first talking about this and she was initially getting data from BioGears, she was like, Austin, this data doesn't look anything like EHR data. It's just so smooth and seems very, you know, like a differential equation. And then we were talking and it was kind of like, oh, well, you know, somebody in an ICU is actually going through a lot of stressors. And in BioGears, actually, your initial patient, you can think of them as just sort of suspended in, you know, nothingness. No stressors, no actions, no movement at all. So when you give somebody a sepsis event in BioGears, but you actually want to simulate an ICU, chances are you probably want to start putting other actions on top of that person. Things like stress, pain, small amounts of exercise, the drugs that they might be getting or not getting, things like that. And then that was that really cool graph that Christie showed where you see the heart rate kind of spiking at different instances. And so you start generating this noisy data because really, like, that patient in an ICU is going through a lot of things and a lot of stressors beyond just whatever their illness is. So this is really great work, I thought. So does anybody have any questions that they would like to bring up? Christie is available to field them. Okay, so William has a couple.
I think that's for you.
Yeah, so I can answer this. William, I unmuted you real quick, but just for everybody else, are there global parameters for posture? So no, there's not. It would be a really cool extension to start having positioning, providing some effects on blood pressure and heart rate, but just right now, there's not. You can kind of think of BioGears suspended in stasis. Okay, so let's see. Okay, so the next thing is our Q&A presentation, but because we've gone over so much, I'm thinking that we will just, unless anybody has any questions that they'd like to be fielded for the next 5 minutes, otherwise we'll just take